Good afternoon. My name is Laura Casas. I'm a chemical engineer and I'm currently finishing my master's in environment and development at Universidad Nacional. Today I'm glad to present the results of my master's degree final project, which is the sustainability assessment of a valorization model of urban used cooking oils in the city of Bogota. I will begin with a brief introduction to the subject, followed by the presentation of the methodology that was proposed for this assessment. I will continue with the results and finish with conclusions. I want to introduce my presentation with this sentence that might describe quite well one of the main motivations of this seminar, and it is that the management of UCO in densely populated cities around the world is very challenging. In Bogota, the main challenging issues are, first, the fact that UCO is being illegally collected to be treated and sold as new oil. Second, that UCO is being poured through sinks and siphons, inducing a series of problems that go from infrastructure damage to pollution of water bodies. And third, that the UCO is also being sent to the sanitary landfill within the solid waste, increasing GHG emissions and lixiviates. And as my colleague Juliana previously explained, different valorization models have been proposed to address this problem. These models consist in exploiting that oil to obtain new products, and in the case of the UCO that is currently being collected in Bogota, this is being used to produce mainly soaps and biodiesel. But even though these models prevent the impacts that originate from those mismanagement practices, well, the required processes to transform UCO into new products also generate environmental and social impacts due to the consumption of resources such as water, energy, and raw materials. Besides, we cannot forget that these valorization models imply transportation of the oil, which requires fuel consumption. So within this context, I want to raise the following questions. First, are these impacts being accounted for? Is the design and implementation of UCO valorization models considering these impacts? And the main question of this work, are these models sustainable? Well, this is actually a common question nowadays, since sustainability is a central topic in the global agenda, and more organizations are trying to achieve sustainability goals. But in this pursuit, sometimes deceptive information about environmental performance, strategies, and motivations is spread through a practice that is known as greenwashing. So in this regard, we should first ask ourselves, what is sustainability? And even though it seems to be an easy question, there is actually quite a wide epistemological debate about this concept. So maybe some of you will immediately relate this word with the term sustainable development. Others will think about the triple bottom line approach, or the three pillars of sustainability, namely the environmental, the social, and the economic. Maybe some of you have even heard about terms like strong and weak sustainability, and perhaps about critical sustainability. But the thing is that there is no general theory of sustainability because we're talking about a discursive concept. So therefore, there are different ways to approach sustainability, and each of these can be justified. But despite the diversity that governs this concept, theorists do agree on the fact that a sustainability assessment must be performed under a life cycle perspective. And here I mean that this is the conceptual core of the different methodologies to assess sustainability. But what does life cycle mean? Well, all the products and services that we consume must undergo a set of stages before and after we consume them. These are, among others, the extraction and transportation of raw materials, the production process itself, the packaging when required, the distribution, the use, the disposal, and in some cases, the reuse and recycling. Different impacts are generated throughout each of these stages, and this is the basis of the sustainability indicators that we have heard lately, such as the environmental footprint, the ecological footprint, the carbon footprint, and so on. Now, for this assessment, a comprehensive conceptual framework was adopted, namely the integrative concept of sustainability. This framework goes beyond the traditional handling of the three dimensions of sustainability and proposes a set of goals and principles. Those goals are securing human existence, maintaining society's productive potential, and keeping options for development and action open. Each of these comprises a set of principles. For the first one, the principles focus on human health, basic needs, autonomy, fair access to resources, and equality in income and wealth. For the second, principles address the use of renewable and non-renewable resources, the use of the environment as a sink for waste and emissions, safety, human and knowledge capital. As for the third goal, principles focus on equal opportunities, societal participation, cultural heritage and diversity, cultural function of nature, and social resources. These allow to understand if a system, a technology, an organization, or even a policy is contributed to sustainability and in a broad and holistic way. So let's move forward to the methodology that was proposed for this work. And here I want to highlight that the objective of this work was to assess the sustainability of an existing UCO valorization model in the city of Bogota, which consists in the production of UCO-based biodiesel. To achieve this goal, three phases were proposed. The first one consisted in understanding and characterizing the study system, as well as defining a reference system. Also, it was necessary to adopt a sustainability approach, which is the integrative concept of sustainability. And in this stage, it was also fundamental to define the project background by performing a literature review on the sustainability of biofuels and waste valorization systems. As for the second phase, which is the core of the methodology, this consisted in defining the assessment criteria, assigning suitable indicators, aligning each criterion with a specific ICO's goal and principle, and defining proper assessment tools. Finally, the third phase consisted in performing the assessment per se, interpreting the results within the ICO's framework, and also carrying out specific analysis to propose improvement scenarios. All of these to finally formulate conclusions and recommendations. Regarding the first phase, I will describe the study and reference systems. So, the study system is the valorization of UCO to biodiesel, and for that purpose, the following stages are performed: collection, pretreatment, and distribution of UCO, and biodiesel production itself. We'll refer to these stages as the life cycle of UCO-based biodiesel. For the first stage, resources for transportation are required. For the second stage, electricity and heat are the required utilities to pretreat UCO and to fulfill certain specifications. And for the study case of this assessment, the stage of distribution is very important because UCO is exported from Colombia to Spain to produce biodiesel. Here, resources for road and ship transport are needed. And the final stage requires the inputs of an industrial process, such as raw materials, the catalyst, utilities, and so on. And for any assessment, it is important to have a reference point to compare the performance of the system of interest. The conventional choice for biodiesel would be fossil diesel. However, since the aim of recycling UCO is to discourage the demand for virgin vegetable oil as other chemical feedstock, palm oil-based biodiesel is chosen as a reference system. It could be another type of virgin vegetable oil, but this would be the most suitable choice since Colombia also exports this oil to Spain and to other countries of Europe for biodiesel production. So for this system, the main stages are cultivation of oil palm tree, the extraction of the oil, distribution of the oil, and production of biodiesel. Again, we'll refer to these stages as the life cycle of palm oil-based biodiesel. And here the first stage is more demanding in inputs since irrigation water, agrochemicals, machinery, and transportation fuels are needed. In the same way, the second stage requires water and raw materials besides the utilities, but still the last two stages are similar to the study system. And for the second phase, which is the core of the methodology, I will mention the selected criteria, the assigned indicators, the ICO's goals, not the principles because of time restrictions, and the selected assessment tools. So for the first goal of securing human existence, the criteria of human health, labor conditions, and work safety were selected. The used indicators were, for human health, fine particulate matter formation and photochemical oxidant formation, and for the other criteria, the level of labor formality and the risk of labor incidents. These were assessed through life cycle assessment and a process of literature review. For the second goal of maintaining society's productive potential, this was very well stocked with 7 criteria, namely water use, demand for fossil resources, economic performance, climate change, water quality, soil quality, and waste management. The assigned indicators were the water stress index, fossil resource use, and for the economic performance from all of the possibilities, the chosen indicator was operating costs associated with the first 2 life cycle stages of the systems. For climate change, we had life cycle GHG emissions, and this might be familiar to some of you since this is the famous carbon footprint. For the other criteria, the indicators were freshwater eutrophication, terrestrial acidification, and the avoided GHG emissions and impacts of waste management. Almost all of these were assessed through life cycle assessment, and even the criterion of economic performance was assessed through a life cycle perspective through the operating expenditure estimation. And finally, for the third goal, which is keeping options for development and action open, the selected criteria were social acceptance, the governmental framework, and the land use change. And the indicators were the degree of public support, the robustness of related government policy and regulations, and the cultural effects of direct land use change, all of these assessed through a process of literature review. Well, now we are ready to continue with the results. And here we have the life cycle impacts or performance of UCO-based biodiesel relative to palm oil-based biodiesel. So a lower value than 100% indicates that UCO-based biodiesel has a lower impact or a better performance than palm oil-based biodiesel, while a higher value indicates the opposite. Here we have the 13 assessed criteria. Each of these aligned with a specific ICO's column principle, as I already explained, but it's important to keep in mind that the criteria were assessed through both quantitative and qualitative indicators, and the qualitative indicators had to be categorized and transformed into numbers. Also, we cannot forget that there is inherent uncertainty in these type of assessments, so this graph only intends to give a general idea of the results. We can see that UCO-based biodiesel has a lower impact or a better performance for almost all of the criteria except for only 3, namely the demand for fossil resources, climate change, and governmental framework. Impacts for these 2 criteria are slightly higher than those of the reference system, and I will later explain why. As for this criterion here, we could say that the set of policies and governmental regulations of palm oil-based biodiesel is twice as strong as the one for UCO-based biodiesel, and that's why we have this bar so high. But in general terms, in the comprehensive terms of the conceptual framework, it is possible to state that UCO-based biodiesel contributes to sustainability by securing human existence, maintaining society's productive potential, and by keeping options for development and action open. I will briefly describe most of the criteria, but first I would like to describe what a hotspot analysis is. So this basically consists in analyzing the contribution share of each of the life cycle stages to the overall impacts or performance. So, as I presented before, these are the stages of both the study and the reference system. But for the graphs I will show you, a common name was designated for each of the stages, namely feedstock sourcing, oil pretreatment and extraction, exportation, and biodiesel production. Let's begin with the first criterion, which is human health. This graph presents the emissions of fine particulate matter of 2.5 microns equivalents produced per 1 ton of biodiesel. We'll start by analyzing the system of interest. So the first stage of feedstock sourcing or UCO collection accounts for 14% of the emissions. The stage of oil pretreatment accounts for only 4%, but the stage of exportation accounts for 63%, and the last one for 19% for a total of over 1 kilogram of particulate matter. If we compare this with the reference system, we will see that emissions are more than twice. Here, the stage of palm oil cultivation accounts for nearly 40% of the emissions. The stage of oil extraction accounts for 32%, the stage of exportation for more than 20%, and the last one for the 8%. So conclusion, the life cycle of UCO-based biodiesel has a lower impact in terms of noxious emissions to air. But let's focus on this value here. 63% of contribution share from the exportation stage. This was observed in most of the criteria that were assessed through life cycle assessment, and it is that without a doubt, the stage of exportation is a major contributor to the overall impacts. So an improvement scenario was proposed, and it was the local production of biodiesel for both systems. And the interest was to explore how the magnitude of the impacts changes if local consumption of these products is fostered. And we can see that when this stage is eliminated, the impact is reduced to about a third, and the hotspot shifts to the stage of biodiesel production. For the reference system, though, the reduction is not as important because the hotspot remains in the cultivation stage. Moving forward to a qualitative criterion, let's talk about labor conditions, specifically the degree of labor formality. In the case of UCO valorization, the registered recycling agents that carry out the operations of collection and pretreatment are legally established companies and are compliant to formally hire their employees. This indicates a good performance, and the only risk lies on the presence of the illegal market, since illegal organizations probably don't follow this kind of regulations. As for the oil palm sector, the National Federation of Oil Palm Growers reports an outstanding 82% of labor formality, which contrasts with a low value of 15% of formality in the rural area. However, it has been found that from the formal jobs, about 84% corresponds to outsourced vacancies, and this could pose some disadvantages, for example, in terms of income. Let's continue with the criterion of water use, which was measured by the Water Stress Index. According to this indicator, production of 1 ton of biodiesel from UCO requires about 10 cubic meters of water. This value is almost 3 times higher for the reference system, as we can see here. Only the cultivation stage requires more water than the whole life cycle of UCO-based biodiesel. For this criterion, the scenario of local production does not display a significant difference, since the hotspot is not located in the exportation stage. Moving forward with the demand for fossil fuels, we could think that without the cultivation stage and the consequent need to produce agrochemicals, UCO-based biodiesel would be less dependent on fossil fuels, but for this specific case, this is not true. Once again, we can see that the exportation stage significantly contributes to the impacts with a 30% of contribution share. So when this stage is eliminated, the system does perform better than palm oil-based biodiesel, but the difference is quite small. So after inquiring to the main hotspot, which is biodiesel production, it's also worth exploring the role of the collection stage and its efficiency in the use of fuel for transportation. I will now continue with one of the most representative assessment criteria, climate change, which was assessed through the indicator of life cycle GHG emissions or carbon footprint. So the results indicate that production of 1 ton of biodiesel generates 600 kilograms of CO2 equivalents, and the exportation stage accounts for nearly half of this value. If we compare this with the guidelines of the Renewable Energy Directive of the European Union, We can see that this value exceeds the recommended value for UCO-based biodiesel. And even though 600 kilograms of CO2 equivalents still represent emission savings in relation to fossil diesel, it's imperative to improve the performance of this life cycle. Now, compared to palm oil-based biodiesel, it's surprising that UCO-based biodiesel generates more GHG emissions. We can see that the cultivation stage has the greatest contribution share in this case, but even if our system avoids cultivation, the contribution share of the exportation stage is very high. If we eliminate this stage, the panorama changes, and performance of UCO-based biodiesel turns better than palm oil-based biodiesel. And if you're familiarized with this subject, you will probably ask yourselves, what about the emissions associated with land use change? Of course, these also have to be accounted for. And these are fundamental because when oil palm is planted on a land with high carbon stocks such as a tropical forest, well, GHG emissions increase a lot and biofuels lose their potential to mitigate climate change in relation to petrochemical counterpart. But when oil palm is planted on a land with low carbon stocks such as pastures or savannas, an oil palm crop increases the carbon stock and the GHG intensity of the derived products is reduced. So this is the case of Colombia, where 80% of new oil palm crops in a specific time period were planted in pastures and croplands. So if we account for these emissions, the GHG intensity of palm oil-based biodiesel becomes negative, and UCO-based biodiesel will still have a worse performance compared to palm oil-based biodiesel. However, recovery of UCO is also preventing the GHG emissions that inadequate disposal practices are generating. And how much are these avoided emissions? Well, this is something we assessed in the criterion of waste management. So it is estimated that 70% of the generated UCO in Bogota is being poured through sinks and siphons, and 20% is being disposed of within the solid waste. Only the 10% is being recovered. If we recall that 1 liter of oil has the potential to pollute 1,000 liters of water, treatment of the polluted volume of water in a wastewater treatment facility would produce 418 kilograms of CO2 equivalents. On the other hand, the degradation of UCO in a sanitary landfill would produce 145 kilograms of CO2 equivalents. If we credit these GHG emissions to our system of interest, the carbon footprint would be less than 50 kilograms of CO2 equivalents. The thing is that, unfortunately, Bogota only counts with 32% of wastewater treatment coverage. This means that an important volume of water polluted by UCO is reaching water bodies, and in this case the main concern is not an increase in GHG emissions, but rather other impacts like water eutrophication, soil pollution, toxicity effects on flora and on fauna. And now that we talk about water eutrophication, this was assessed for the criterion of water quality. If I show you the eutrophication potential associated with the production of 1 ton of UCO-based biodiesel, we cannot even see the contribution share of each stage properly because the eutrophication potential associated with palm oil-based biodiesel is more than 8 times higher. This, of course, is due to the use of agrochemicals in the cultivation stage. So even if we consider the improvement scenario of local production of biodiesel, we will still conclude that our system of interest performs significantly better. A similar analysis can be done for the criterion of soil quality, which was assessed through the acidification potential. The performance of UCO-based biodiesel is much better than that of palm oil-based biodiesel, as we can see here, and this shows that activities of crop cultivation are detrimental in terms of resources quality. For this criterion, the exportation stage does have a great contribution share, so the improvement scenario shows an important reduction, and the comparative advantage in relation to the reference system becomes greater. Moving forward to the criterion of economic performance, production costs for the first two stages of the life cycle were estimated. So here I present the costs of producing 1 ton of pretreated UCO and 1 ton of crude palm oil ready to be exported for biodiesel production. In the first case, if we account for the buying of the UCO, the costs of transportation, and also the personnel costs and the operating costs of the pretreatment facilities, we get a value of 1,300,000 Colombian pesos, which are about 360 US dollars. In the second case, this value differs widely depending on the area, but if we account for the costs of irrigation, agrochemicals, maintenance of machinery, phytosanitary management, transportation, operating costs of the oil extraction facilities, and personal costs, we get a value of 1,500,000 Colombian pesos, which are about 420 US dollars. The system of interest performs better, and even though the difference might seem small, since we're talking about a commodity, this value poses an important comparative advantage for UCO. And even though I would like to dig deeper into further criteria, I will finish my analysis with the criteria of social acceptance and land use change. The first one was analyzed by exploring the degree of public support, and a proper assessment of this criterion would actually require proper research methodologies such as structured interviews and fieldwork. But in general terms, the idea of recovering waste to produce useful products makes UCO valorization an appealing alternative. And since it's conceived in the framework of environmentally friendly initiatives in the city and the promotion of circular economy models, UCO valorization does count with public support. In the case of palm oil exploitation, there is a global phenomenon of rejection to this feedstock, considering the effects on diversity due to the deforestation that have been widely advertised. And even though that is not the case in Colombia, because as I explained before, oil palm is not contributing to deforestation, it is hard to break this stereotype. So with this, I conclude my presentation with the following conclusions. When analyzed from a life cycle perspective and a holistic approach, valorization of UCO to produce biodiesel does contribute to sustainability. In relation to oil palm-based biodiesel, UCO-based biodiesel has a lower impact or a better performance in 10 out of 13 assessed criteria. And even though the system of interest has a higher impact in terms of GHG emissions compared to the reference system, considerable savings in GHG emissions are achieved in relation to fossil diesel. Also, by preventing inadequate disposal practices, UCO valorization prevents a significant amount of GHG emissions, as well as other impacts on water quality, soil quality, and biodiversity. And if UCO is used as a feedstock for local production of biodiesel or other oleochemicals, the magnitude of the environmental impacts is reduced, since the exportation of this feedstock has a high contribution share in the overall impacts. So thank you very much, and I will gladly answer the questions you have.